For this parabola, it's we don't have the same steepness at all points. You know, for example, we have a different steepness here. It's flat, and over here we have a different steepness, negative slope. You know, we have different steepness for every single point. Okay, guys, have any questions? All right. So, we're going to look at another example. We're going to find the derivative of the square root of x function, and we're going to find the equation of the line that is tangent at the point where x equals to 2. All right. So number one, to find the derivative, f prime of x, rather, that's the limit of f of x plus h minus f of x over h as h approaches 0. Now, so the first term calls for a function f of x plus h. That is, whenever you see the letter x, replace with x plus h, and then subtract the original function f of x and divide that by h. Now, if we try to compute this limit using what we usually call the replacement theorem, which is really direct substitution, well, let's see what we get. So let me use a different color. So that's the square root of x plus 0 minus root of x over 0, which is root of x minus root of x over 0. And isn't that a 0 over 0? Which is good. It's great, because that means that there is a numerator and denominator that will get canceled. We get rid of this, you know, this indeterminate form, and then we will be able to find the actual limit. Well, the tricky part here is how do we manipulate this expression so that we can simplify this? Well, of course, we have radicals. Factoring, it's not going to work here. Alright, so we need to think of something else. So factoring is not going to work. Maybe, well, rational, no. Complex fractions, no, it's not going to work either. Well, let's think of something else. Any ideas what to do? We already did something involving radicals before, in fact. Multiply by the conjugate of the numerator in this case. So, that is, multiply by root of x plus h minus plus root of x and divide by root of x plus h plus root of x. Alright? Okay, I'm gonna make some space over here. And of course, there's a couple of ways to simplify this numerator. So number one, foiling, that's number one. But did you see how many multiplications are we required to do? That's like, if you want to do it that way, do you feel more comfortable with the following, with the foiling method? That's fine. However, how about seeing this as a minus b times a plus b? Isn't this the factored form of a difference of squares? So, what we're going to do here is f prime of x is the limit of quantity squared, that is radical x plus h squared minus, that is a squared minus b squared. But we're doing the difference of squares backwards in this case, right? And the whole thing, let's divide that by, just multiply this across. H times square root of x plus h plus root of x. And I know what you might be thinking over here. Yeah, you might be thinking that it would be a good idea to distribute the h, right? Don't distribute. And we already discussed the reason for this, because the example that we did for plain limit without this x and h, it worked the same. Don't distribute. But I'm gonna stress on this again, just so it resonates to you all the time. So number one, cancel the square with the radical. We get limit of x plus h minus cancel the other radical with the square on the second term, that is x, and over h times the square root of x plus h plus root of x as h approaches 0. Now check this out. These x's right here are going to get canceled, and that's going to give us limit of h in the numerator over h over h times the square root of x plus h plus root of x as h approaches 0. So this is the reason why you don't want to distribute this, because if you distribute this, you will get this, you know. Let me check this out. H root of x plus h plus h root of h, root of x. And in this case, you wouldn't be able to see how these h's cancel. Alright? So cancel the h's. And at this point, we already canceled those factors, or rather that quotient that creates the indeterminate form 0 over 0. I already erased it. So that means we're left with the limit h approaching 0, 1 over the square root of x plus h plus the square root of x. And at this point, if we compute the limit for h approaching 0, well, x plus 0 is just going to be x. Well, for now, let's write it down as x plus 0. And at this point in the limit, we no longer write the limit symbol. That's precisely at the moment where we plug in the value. But throughout the exercise, we need to write the limit symbol all the time. So x plus 0, that's simply 1 over square root of x plus root of x, and the denominators are like terms, that's 2 root of x. So that's the derivative f prime, and this expression will be used to find the equation, the slope at every single point in the function. Well, actually they're asking us to find the slope and the equation. Let's see, square root of 2, okay, at 2. So number one, we need to find a point. So f of x equals square root of x. That means f of 2 equals the square root of 2. That means the point 2 comma root of 2. So we are going to use the expression that we obtained, this derivative, via limit definition to find the slope. Okay, so that's one number piece of information. The other one is the slope, which is the derivative, and that's 1 over 2 root of x. So if we evaluate the derivative, well, let me move it to here. So if we evaluate this derivative at 2, we're going to get 1 over 2 root of 2. And you might want to rationalize this number, the denominator, so that's the square root of 2. Root of 2 times itself, it's going to be 2 times the 2, it's going to be 4. So now that we have all the pieces of information, we can find the equation of the line that is tangent to the graph of square root of x at the point 2 comma root of 2. And we can get that by using the point slope formula, the point slope form. So y minus y1, that's root of 2, equals m times, which is root of 2 over 4, x minus x1, which is 2. And well, there's really nothing to simplify over here. I would leave it like this because we're gonna have crazy numbers to combine, so no need. What is this essentially? Picture for this. So we have the graph of the square root of x, which looks like this. And at the point, so 1, 2, 3, 4, 5, so 2, this is the point 2 comma root of 2. We're going to have this line that is tangent, which happens to be that linear equation, right? In other words, we're also finding the steepness of the graph square root of x at this point, which if you look at this curve, the steepness is not the same, right? Let's look at another example. So at the beginning of constructing the idea of the average rate of change versus instantaneous rate of change, we were looking at one word problem describing the position of a car, for example. And well, the thing is, when we move from point A to B, for example, from San Diego to LA, and we do maybe, what is it, 2.5 or 2 hours and a half, and roughly at a speed of what about 70 miles per hour? I mean, considering there's no traffic, which is not usually the case. Well, this velocity, or rather this speed right here, is the average velocity. It's not the instantaneous velocity, because, well, you will go through different places on the freeway for which there's traffic. You'll have to slow down, and then you will be able to speed up when there's no traffic. So we want to find the instantaneous velocity. The velocity here, the velocity there, the velocity there. So we will no longer have to use the average rate of change. We will be able to use now the instantaneous rate of change. In this case, the derivative. So we're given the function that provides the position of the car at different